Welcome to the Sleepy Scientist. It is wonderful to have you here. Before we start, I would love to know where in the world you are watching from tonight. Maybe a quiet bedroom, a calm train ride, a cozy couch with warm tea. Wherever you are, I hope you are safe, comfortable, and ready to slowly drift into thought. If you like these relaxing explorations and want more, a like and subscribe really helps this small sleepy channel float along. To those already subscribed, thank you. Your support means more than you know. Now I will try not to make tonight's topic so interesting that it keeps you awake, but if it does, at least you will understand why particles sometimes act like waves and why reality seems to hesitate until someone is watching. A small price to pay for a restless night. So let's begin. What is quantum physics and why does it sound like the universe is making things up as it goes? The world we know, the one we can see and touch, feels solid and predictable. If you drop a teacup, it falls. If you flip a coin, it lands. If you close your eyes, the moon does not vanish. But in the early 20th century, scientists looked closer, much closer, and the deeper they looked into matter, the stranger things became. They found light could behave like both a wave and a particle. Particles could be in many places at once until they were measured, and observing something did not just show what was there, it seemed to change it. This was not bad data, it was real and reproducible, and it shattered the tidy rules of classical physics that had lasted for centuries. Quantum physics was not just a new branch of science, it was a new way to see reality. A shimmering world where certainty is replaced by probability and cause does not always come before effect. In this video we will drift through that world. No need to grasp every equation or remember every name. We will go slowly, softly, one mystery at a time. From the earliest puzzles that pushed scientists off their classical perch to the modern questions that still keep physicists awake at night. So tuck yourself in, close your eyes if you like, and let's explore a world where even emptiness is not empty and where everything you thought you knew about reality is only probably true. At the turn of the 20th century, physics felt almost complete. Motion laws were understood, thermodynamics was neat, light was explained in electromagnetic theory. It was a golden age of certainty. Some scientists thought all big questions were answered. Only a few odd bits remained like dust in the corners of a swept room. One dusty corner was a simple idea. What happens when you heat an object? Warm metal or coal glows red, then orange, then white, depending on temperature. This glow, called black body radiation, comes from how objects emit electromagnetic radiation when heated. It seemed simple to explain, but the math refused to work. Classical physics predicted that as the temperature rose, the object should give more and more energy at shorter wavelengths, especially ultraviolet. The problem was this meant infinite energy at high frequencies. An impossible idea nicknamed the ultraviolet catastrophe. No tweaking could fix it. Something was missing. Then came Max Planck. In 1899 he was a German theoretical physicist known for careful thinking, not radical but pragmatic. When faced with the black body problem, he did something revolutionary. He suggested energy could not be emitted in any amount but only in tiny, indivisible packets, like coins you cannot split, the smallest units of energy. He called them quanta. This was a big change from the smooth continuous energy view. Instead of flowing smoothly, energy came in steps based on radiation frequency. Planck introduced a constant now called Planck's constant to describe the packet size, unimaginably small but mathematically elegant. When he used this idea, the infinite energy problem vanished. The equations worked and matched reality. Planck had solved the catastrophe, yet he did not fully believe it. He saw it as a math trick, not a true picture of the universe. He thought future physicists would find a better explanation. He could not know his trick would become the base of quantum theory and change physics forever. His idea that energy comes in discrete packets laid the foundation for a theory that would undo much of classical thinking. At the time it felt like a side note, not a revolution. Planck only wanted the math to work, but he lit the first match in a slow-burning fire that would reshape our understanding of light, matter, and reality itself. Published quietly in 1900, it did not shout its importance, just a small constant, a new energy idea, and a fix for a stubborn problem. From then on, physics would never feel finished again. By the early 1900s, light was thought to be well understood. Thanks to James Clerk Maxwell's equations, scientists had shown that light behaved like a wave. It bent, bounced, diffracted, and interfered like any proper wave. After Max Planck's quiet idea of energy quanta, most physicists assumed things would settle into a slightly adjusted normal. But then came a riddle with metal, light, and a strange refusal to cooperate. It was called the photoelectric effect. It worked like this: shine light on a metal surface and electrons can be ejected. It made sense. Light brings energy. Energy kicks out electrons. According to wave theory, making the light brighter should increase the electron's energy, but experiments showed something strange. Brighter light did not always eject electrons with more energy. What mattered was the light's frequency. If it was below a certain frequency, no matter how bright it was, nothing happened. But above that frequency, even a dim beam could knock electrons free. This sharp threshold made no sense for wave theory. This mystery brought Albert Einstein in 1905. In his miracle year, he explained the effect by suggesting light was not just a wave. Sometimes it acted like a particle, a tiny bundle of energy traveling in a straight line. He called these packets quanta of light, later known as photons. Each photon's energy depended on its frequency. If a photon had enough energy, it could knock an electron loose. If it did not, no amount of them could do it, like trying to open a locked door with keys that do not fit. Einstein built on Planck's work but went further. He said light itself was made of these packets, not as a trick but as reality. Many physicists resisted this particle idea because light clearly showed wave behavior like diffraction and interference. Einstein did not deny the wave nature. He proposed light was both a wave and a particle, acting like one or the other depending on how you observe it. This was not a perception trick, it was fundamental to light. Imagine sunlight through a window spreading like a wave, but zoom in far enough and you find tiny energy quanta hitting atoms one by one. Wave-particle duality is one of the strangest ideas in physics because it breaks our categories. In the classical world, things are particles or waves, not both. But the quantum world does not ask for our logic. Einstein's photon explanation matched experiments beautifully. Photon energy depended on frequency just as Planck suggested. It explained why low-frequency light, no matter how intense, could not eject electrons. The photons simply lacked enough punch. This discovery was so important Einstein got the 1921 Nobel Prize in Physics for it, not for relativity. Yet even he was uncomfortable with quantum theory's later probabilistic ideas, saying God does not play dice with the universe. Dice or not, the rules were changing. Light refused to fit into neat boxes. It came in quanta, danced as a wave, collided like a particle, and shimmered between states, enough to keep us wondering and unsure. What began as a simple experiment ended up shaking the foundations of physics, because if light could be both continuous and discrete, what else in the universe might be breaking the rules? Imagine setting up a table, placing a flashlight at one end and cutting two tiny slits in cardboard. Shine the light through and look at the screen behind. Not exciting, but inside this setup lies one of the most mind-bending experiments in science, the double-slit experiment, famous not for complexity but for what it reveals. In classical physics, waves and particles behave differently. A wave spreads and interferes with itself like water through two openings, making a pattern of peaks and troughs. Particles, like rubber balls shot at two openings, make two impact clusters behind them. When scientists shined light through two slits, it acted like a wave, making an interference pattern. Then they turned the light down to send one photon at a time. You would expect particles to act like balls, but instead over time the photon still built an interference pattern as if each photon interfered with itself. It seemed to go through both slits at once. Stranger still, when detectors were placed at the slits to see which way it went, the interference vanished. The photons acted like particles again, as if observation forced them to choose left or right. Turn off the detectors and the pattern returned. This showed it was not disturbance from measuring but the knowledge of the path that changed the behavior. Reality seemed to care if it was being watched. This has been repeated with photons, electrons, even large molecules, and the result is always the same. Unobserved they act like waves, observed they act like particles. This sits at the heart of quantum physics, showing that particles exist as possibilities until measured. Some say the particle's wave function is a tool for predicting outcomes, others imagine each possibility happens in a separate universe, but whatever the interpretation, until we observe it, the particle does not commit. The double-slit experiment turns a simple setup into a deep mystery about whether observation shapes reality itself. It leaves us with the thought that the universe at its core is a strange tapestry of possibilities that responds to our gaze. In quantum physics, if there is one piece of math whispered through the entire theory like a quiet spell, it is Schrödinger's equation. Do not worry, this is not a math lecture. No one dreams about partial differential equations, but this equation is different. It is like the heartbeat of the quantum world. In the 1920s, physicists struggled to describe particles that did not act like particles. Electrons showed wave patterns. Photons acted like ghosts of probability. Newton's laws could not explain it. The universe needed a new language. In 1926, Erwin Schrödinger proposed an equation describing not just how particles moved but how their wave functions changed over time. It looked complex but told a simple story. It showed how a quantum system changes. The key idea is the wave function. Think of it as a mathematical whisper telling us everything possible about a quantum system. Where a particle might be, how likely it is to be there, how it might move. It does not give hard answers. It gives probabilities. In classical physics, a particle is a dot with an exact position and speed. In Schrödinger's world, it is a rippling cloud saying the particle is likely here but could also be there. The equation lets this cloud shift and flow over time, showing how possibilities move. When we measure the particle, the wave function collapses. The cloud disappears and we get a single definite answer only after looking. This view is very different from the mechanical universe of planets and paths. Instead, we see fields of probability full of uncertainty until observation pins them down. Imagine you are blindfolded in a room with a quiet cat. You toss balls to hear where they land and build a picture of where the cat might be. That picture is like a wave function. Now imagine an equation telling you how your picture changes over time. Schrödinger did that for electrons. The equation is smooth and continuous, letting waves of probability ripple like water. It respects energy conservation and time flow but does not care about certainty. It tells what could happen, not what will happen. It works beautifully explaining atoms, molecules, semiconductors, superconductors, and even quantum tunneling where particles pass through barriers. One famous success was explaining the hydrogen atom. Before quantum mechanics, no one understood why electrons stayed in specific orbits. Schrödinger's equation showed electrons form standing waves, stable patterns of probability called orbitals, drawn as clouds in textbooks. These are real measurable likelihood zones where electrons may be found. They exist because the electron is a ripple in a probability sea. The equation has aged well, predicting small-scale behavior with accuracy, yet it is abstract. You cannot hold a wave function, but it is there, describing potential from an atom in your tea to your phone's electronics. There is also a philosophical side. Is the wave function a description of our knowledge or something real that exists until collapse? Physicists debate this. Schrödinger himself disliked the idea that particles had no definite properties until observed. His famous cat thought experiment was meant to criticize that uncertainty. He gave us the math for quantum waves, then questioned what they meant. Still, his equation remains a quiet guide to what could be. It does not shout, it flows, showing a universe that is subtle and mysterious. At tiny scales, motion is not always motion, position is not always position, certainty is rare, but thanks to one elegant equation we can still navigate the haze. In the classical world of apples, bicycles and bowling balls, you can know where something is and how fast it is going at the same time. A radar gun can clock a car's speed while GPS tells its position. No mystery, but the quantum world does not follow these rules. In the 1920s, Werner Heisenberg introduced a strange and central principle of quantum mechanics called the uncertainty principle. It says the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Momentum is mass times velocity. In everyday life this seems silly because you can see a train and know both position and speed, but at the quantum scale this clarity is impossible. It is not about clumsy tools or bad technology. The uncertainty is built into reality itself. Imagine trying to see an electron's position and speed. You shine light on it. Light has photons that carry energy. When one photon hits the electron, it changes its motion, like throwing tennis balls at a soap bubble in the dark. You will find it but change it too. Still, Heisenberg's principle is deeper than disturbance. Even with a ghostly non-touching observation, the uncertainty is there. It comes from the wave nature of particles. A wave stretches through space, so you cannot pinpoint its position without losing information about its momentum. A wide smooth wave gives poor position accuracy but good momentum accuracy. A narrow wave gives sharp position but messy momentum. It is a trade-off. The product of position uncertainty and momentum uncertainty is always greater than or equal to Planck's constant divided by 4 pi, a tiny number, so in daily life it does not matter, but for electrons, atoms and subatomic particles it shapes behavior. If you trap a particle in a small space to fix its position, its momentum becomes wild. The more you confine it, the more it resists. Nature refuses perfect location knowledge. It is like holding mist, squeeze tightly and it slips away. This principle also explains why atoms do not collapse. If electrons fell into the nucleus, their position would be exact and their momentum uncertainty infinite, needing infinite energy, so they cannot sit still. Uncertainty also applies to pairs like energy and time, or angular momentum and orientation. More precision in one means less in the other. It is not chaos but a structured blur that gives the universe texture. It lets particles tunnel through barriers, keeps atoms stable, and makes chemistry possible. Without it, reality might be too rigid for life. Science has always chased certainty, but Heisenberg showed that some truths are always out of reach. This is not failure but nature's way. Uncertainty invites us to accept the blur. The deepest truths are often cloudy and unresolved. In the classical world, a coin lands heads or tails, a switch is on or off. But in the quantum world, objects do not always pick one state. They can exist in a mix of all possible states. This is quantum superposition. Imagine flipping a quantum coin. It is not secretly one side waiting to be seen. It is genuinely both heads and tails until observed. When you check, it chooses a state and becomes real. Before that it was both. Superposition first described particles like electrons and photons, which exist as wave functions containing all possible states until measurement selects one. Picture a fog of outcomes. The particle is smeared across every path it could take. When you interact with it, the fog snaps to a single point, like lightning lighting one hill in mist. This inspired Schrödinger's cat thought experiment. A cat in a sealed box with a radioactive atom. If the atom decays, poison is released. Quantum mechanics says the atom is in both decayed and not decayed states until observed, so the cat is both alive and dead. Schrödinger used this to show the absurdity of applying quantum rules to large objects. Yet the idea became a symbol of quantum indeterminacy. Superposition is not a flaw, it is a powerful feature used in quantum technology. In quantum computing, the basic unit is a qubit, which can be both 0 and 1 at the same time. A single qubit holds more information than a classical bit, and entangled qubits can represent many states at once, allowing some problems to be solved much faster than classical computers. Superposition is also used in quantum cryptography and sensing. But it is delicate. Any interaction with the environment, like stray photons or vibrations, can collapse it. This fragility, called decoherence, is a big challenge in building stable quantum systems. It shows that quantum power works only in precise conditions. Superposition also raises questions. Is it reality or just our knowledge? Some say the wave function represents our best guess until measurement. Others say it is physically real until forced to choose. Either way, it tells us opposites can coexist, and reality is a tapestry of possibilities overlapping until observation pulls one thread. It is strange and beautiful, giving us a universe that is flexible, not rigid, poetic, not mechanical, allowing contradiction and uncertainty as features, not flaws, and opening new ways to compute, communicate, and explore when reality will not make up its mind. Imagine you have two gloves, one left-handed and one right-handed. You put each glove in a separate box and send one far away. You do not know which box has which glove, but the moment you open one and see a left glove, you instantly know the other is right. This is simple logic because the gloves were decided from the start, but quantum entanglement is not like that. Entangled particles are like gloves that do not decide which hand they are until after you open one box and whichever you open. somehow tells the other what to be instantly no matter the distance. The properties do not seem to exist until you measure one and that measurement instantly affects the other. Entanglement happens when two particles are created or interact in a way that links their quantum states. Whatever happens to one affects the other even far apart. Imagine two entangled photons with uncertain polarizations. One may end vertical, the other horizontal, but they do not decide ahead of time. They remain in a shared superposition until measured. When you measure one, the outcome becomes definite and the other becomes definite too instantly, no signal, no delay. If one photon is measured in Paris and the other in Tokyo, both update at that moment. Einstein called this spooky action at a distance. He did not like it because relativity says nothing travels faster than light, and he believed in locality where one place cannot instantly affect another. In 1935, Einstein, with Boris Podolsky and Nathan Rosen, argued that if quantum mechanics allows this, it must be incomplete and that hidden variables must decide the outcomes. But in the 1960s, John Bell created a way to test this with Bell's theorem, showing how to tell the difference between quantum predictions and hidden variables. Experiments have repeated this many times and quantum mechanics wins. Entangled particles act in ways no local hidden variables can explain. The results are random but perfectly correlated, like two people flipping coins on opposite sides of the galaxy and always getting opposite results without knowing which until they flip. This does not let us send messages faster than light because the results are random and you cannot control them. Entanglement's connection does not weaken with distance. Particles have been entangled over hundreds of kilometers and the effect still holds. What entanglement truly is remains debated. Some say it is about information we know, not the system itself. Others say it shows a deep non-local reality. Some even think spacetime might come from networks of entanglement. This is bold but still studied. Entanglement is used in quantum teleportation, which moves quantum states, not objects, in quantum key distribution for secure communication where eavesdropping breaks the entanglement and is detected, and in quantum computing where entanglement lets many qubits work together in ways classical bits cannot, making operations more powerful and connected. This spooky action is now a tool for advanced technology, showing the universe is a web where distant things can be part of one whole. At tiny scales, this silent partnership is everywhere, reminding us that even in a vast universe there are invisible threads tying things together. Schrödinger's cat is one of the most famous ideas in physics. It became the symbol of quantum mechanics' strangeness. In the 1930s, physicists debated what quantum theory really meant. The math worked, but what was it saying? Was the wave function real? Did particles exist in multiple states until measured? Schrödinger, already famous for his equation, was skeptical of applying superposition to big objects, so he imagined a cat in a box with a radioactive atom, a detector, and poison. If the atom decayed, the poison would be released and kill the cat. If not, the cat would live. Quantum mechanics says until you observe the atom it is both decayed and not. So the cat is both alive and dead. Schrödinger never meant this as a real experiment. He used it to show the absurdity of the idea, but it became a lasting metaphor for unmeasured systems. Before measurement, a quantum system exists in a cloud of probabilities. Measurement collapses it to one state, but what counts as a measurement is debated. Is it conscious observation, a detector, or the environment? Different interpretations give different answers. The Copenhagen interpretation says the wave function only describes what we can say about a system and collapses when measured. The many worlds view says the cat is alive in one branch and dead in another and both happen. Decoherence theory says the cat gets entangled with so many variables in the environment that the superposition becomes inaccessible. Schrödinger's cat forces us to face the gap between the predictions and our picture of reality. It shows that quantum systems evolve through all possibilities until something forces a choice. Whether that choice is real collapse or just our path through the multiverse is still unknown. The cat is not just about life and death, it is about how reality and observation are tied, and how in the quantum world certainty is rare and the universe sometimes waits for us to look. By the late 1920s, quantum mechanics was already splitting into different interpretations of what the strange math really meant. One of the most widely taught was the Copenhagen interpretation shaped by Niels Bohr and Werner Heisenberg. It said the wave function is not a physical thing but a tool to calculate probabilities. Before measurement, a system has no definite properties. Measurement forces it into a single outcome. Bohr emphasized complementarity, the idea that quantum systems can show particle-like or wave-like behavior depending on how we look. Both are needed for a full picture but cannot be seen at the same time. Heisenberg's uncertainty principle fit neatly here. The act of measuring one quantity precisely blurs the other. The Copenhagen view is pragmatic. It does not claim to tell what reality is, only what we can say about it. Critics like Einstein disliked this. Asking if the moon is there when no one looks, Bohr replied that physics is about what we can say about nature, not how nature is. This left room for mystery but kept the focus on experiment and prediction. Still others wanted a clearer picture. This led to rival interpretations. One was the many worlds interpretation proposed by Hugh Everett in 1957. Instead of collapsing the wave function, it says all possible outcomes happen. The universe splits into branches, each containing a different result. In one branch the photon goes left, in another right. We only experience one branch but the others are equally real. There is no randomness, only branching. This removes the need for collapse but at the cost of an endless number of universes. Some find this elegant, others unsettling. Another is the pilot wave theory, originally by Louis de Broglie and developed by David Bohm. Here particles always have definite positions guided by a wave that evolves according to Schrödinger's equation. The wave determines the probabilities but the particle's path is real. This restores determinism and removes collapse but requires a non-local guiding wave. Decoherence is another approach explaining why we do not see superpositions in daily life. Quantum systems constantly interact with their environment, which entangles their states and spreads the information so widely it is effectively lost. The superposition is still there but becomes inaccessible. Decoherence does not solve the measurement problem by itself but shows how classical reality emerges from quantum possibilities. Quantum mechanics works perfectly in practice but its meaning is still debated. Each interpretation gives a different story but the same predictions. It is like looking at the same map with different legends. The roads match but the explanations differ. In the 20th century, the quantum revolution did not just change physics theory, it began to reshape technology. Quantum mechanics explains the stability of atoms and the structure of the periodic table. It underlies chemistry and materials science. It made possible the invention of the transistor in 1947, which led to modern electronics. Without quantum theory there would be no computers, smartphones, or internet. It also gave us the laser in 1960, a device that uses quantum-stimulated emission to produce a narrow beam of light. Lasers are now in everything from barcode scanners to surgery. Quantum mechanics is behind magnetic resonance imaging in medicine, superconductors that carry current without resistance, and semiconductors that power solar cells. It explains nuclear power and the operation of LEDs. It allows atomic clocks so precise they lose less than a second in millions of years, which makes GPS navigation work. Today a second quantum revolution is underway with technologies that use superposition and entanglement directly. Quantum computers promise to solve problems that would take classical machines centuries. Quantum cryptography offers secure communication based on physics, not math. Quantum sensors can detect tiny changes in gravity or magnetic fields. These tools are still developing, but the potential is enormous. From understanding the universe to building new devices, quantum mechanics has become both a key to nature's rules and a toolbox for innovation. It is strange and abstract yet practical and essential, showing that even the most mysterious ideas can become the most useful, and that sometimes accepting uncertainty opens the door to certainty in what we can create. Quantum mechanics may seem distant from daily life, but it quietly shapes much of what we use and see. At its core it describes the smallest building blocks of matter and energy and how they interact. Atoms are not tiny solar systems with neat planets orbiting a sun. Instead, electrons exist in cloud-like regions called orbitals. These clouds are shaped by the solutions to Schrödinger's equation and defined by quantum numbers that describe energy, shape, and orientation. The structure of these orbitals explains the periodic table, why elements in the same column behave alike, why some are metals and others gases, why sodium reacts violently with water while neon does nothing. Chemistry is quantum rules in action. Bonds between atoms form when electrons are shared or exchanged, and the shapes of molecules come from quantum constraints on electron positions. Without these rules, life's molecules like DNA and proteins could not form stable shapes. Quantum mechanics also explains why some materials conduct electricity and others do not. In conductors, electrons can move freely through energy bands. In insulators, a large gap separates filled and empty bands so electrons stay put. Semiconductors like silicon have a small gap that can be bridged by adding energy from heat or light. This is why they are used in transistors and solar cells. Quantum tunneling. Another strange effect happens when a particle passes through a barrier it should not cross. In classical physics, a ball cannot roll over a hill taller than its energy, but in quantum mechanics particles have a probability cloud that can extend through barriers. Sometimes they appear on the other side without enough energy to climb over. Tunneling powers the sun's fusion reactions and is used in devices like tunnel diodes and scanning tunneling microscopes that image atoms. Superconductivity is another quantum effect. In some materials cooled near absolute zero, electrons pair up and move without resistance, creating powerful magnetic fields and lossless currents. This is used in MRI machines and maglev trains. Superfluidity occurs when certain liquids flow without friction, climbing walls and never settling. These are macroscopic quantum states where many particles act as one wave. Quantum mechanics even affects color. The way atoms absorb and emit light depends on discrete energy levels. Photons are absorbed when their energy matches the gap between levels. This is why heated objects glow red then orange, then white. It is why leaves are green and the sky is blue. At the smallest scales, quantum electrodynamics describes how light and matter interact with incredible precision, matching experiments to many decimal places. This is one of the most accurate theories in science, yet quantum mechanics is not complete. It does not include gravity. Einstein's general relativity explains gravity as the curvature of spacetime caused by mass and energy. This works well for planets and stars but breaks down at the quantum scale. Combining quantum mechanics and relativity into a theory of quantum gravity is one of the great challenges in physics. Approaches like string theory propose that particles are tiny vibrating strings whose modes give different particles. Loop quantum gravity tries to quantize spacetime itself into tiny loops. Neither is proven. Experiments may one day reveal the right path. Black holes are where quantum mechanics and gravity collide most dramatically. They are regions where gravity is so strong nothing can escape, yet Stephen Hawking showed they emit faint radiation due to quantum effects near the event horizon. This Hawking radiation means black holes can slowly evaporate, raising questions about what happens to information that falls in. This touches the black hole information paradox, another deep puzzle. Quantum field theory extends quantum mechanics to fields filling space. Particles are excitations of these fields. The standard model of particle physics is a quantum field theory describing all known particles and forces except gravity. It unites electromagnetism, the weak nuclear force, and the strong nuclear force, predicting particles like the Higgs boson, which was found in 2012 at CERN, yet it leaves mysteries. It does not explain dark matter, dark energy, or why there is more matter than antimatter. Quantum mechanics opened the door to these questions by showing the universe is stranger and richer than classical physics imagined. It is not just a theory of the small but a foundation for understanding the large. From the way stars shine to the way your phone works, it reminds us that reality is built from probabilities, waves, and particles that sometimes act like both, and that at every scale there is more to learn. The quantum world is not just a curiosity, it is the fabric of everything. The quantum world might feel far away, but it is not locked in labs. It touches your life in quiet, constant ways. When you swipe a credit card, scan a barcode, make a video call, or listen to music through noise-canceling headphones, you are using technology built on quantum principles. Noise canceling works by detecting incoming sound waves and creating opposite waves to cancel them. Microphones and processing chips rely on transistors. Transistors exist because of quantum mechanics. They control the flow of electrons in semiconductors. Your phone's processor holds billions of these switches on a chip smaller than your hand. Quantum theory also powers LEDs, which emit light when electrons jump between energy levels. The color depends on the gap between levels. LEDs use less energy than incandescent bulbs and last longer. Lasers, born from quantum-stimulated emission, are in DVD players, optical fiber networks, laser printers, and eye surgery. Quantum mechanics also enables superconducting magnets in MRI machines, letting doctors see inside the body without cutting. GPS navigation works because satellites carry atomic clocks that count vibrations of atoms with quantum precision. Without these corrections, GPS would be wrong by kilometers each day. Solar panels rely on the photoelectric effect explained by Einstein. turning sunlight into electricity by freeing electrons in a semiconductor. Quantum tunneling makes flash memory work. Electrons tunnel into and out of traps to store bits. Tunneling also appears in the scanning tunneling microscope, which can image individual atoms. Quantum cryptography uses entanglement and superposition to make secure communication where any eavesdropping is detectable. This is already being tested for financial and government use. Quantum computing is emerging using qubits that can be both 0 and 1, allowing some problems to be solved far faster than classical machines. Quantum sensors can measure tiny changes in gravity, magnetic fields, or time, useful for navigation without GPS or detecting underground structures. The second quantum revolution is about controlling quantum states directly rather than just using quantum-explained effects. This requires precise isolation from noise and advanced error correction, but progress is steady. Beyond technology, quantum mechanics changes how we see reality. It teaches that the world is not made of solid objects moving on predictable paths, but of possibilities that take shape when measured. It challenges our ideas of cause and effect, locality, and even existence. It suggests the universe might be connected in ways we cannot see, that particles can be linked across galaxies, that emptiness seethes with activity, and that certainty is an illusion we build from limited information. The philosophical impact has inspired debates, books, art, and films. From science fiction to deep metaphysics, some see quantum mechanics as proof that consciousness plays a role in reality. Though most physicists treat consciousness as just another physical process, still the language of quantum has entered everyday culture, often misused but reflecting a fascination with the idea that the world is stranger than it seems. Quantum theory also influences other sciences. In biology, quantum effects may help plants in photosynthesis, moving energy with near-perfect efficiency. Birds might use quantum entanglement in their eyes to sense Earth's magnetic field for navigation. Enzymes may use tunneling to speed reactions. These ideas are part of quantum biology, a young but growing field. In cosmology, quantum fluctuations in the early universe may have seeded galaxies. Inflation theory uses quantum fields to explain the rapid expansion after the Big Bang, and the cosmic microwave background holds patterns from quantum processes stretched to cosmic size. Quantum mechanics is both a theory of the smallest scales and a key to the largest, connecting the subatomic to the cosmic. As we explore it, we are not just learning how to build faster computers or sharper sensors, we are uncovering the rules that make stars shine, planets form, and life possible. It is a reminder that mystery and utility can live in the same theory, that what begins as abstract equations can become the engine of modern life, and that the more we learn about the quantum world, the more we realize how much is left to discover. Quantum mechanics began as a desperate fix for problems classical physics could not solve, but it has grown into one of the most successful theories in science. Its predictions match experiments to astonishing accuracy. It has survived every test for more than a century, yet it remains deeply counterintuitive. One reason it works so well is that it is built on mathematics that describes probability rather than certainty. The wave function contains all possible states a system can have and evolve smoothly over time according to Schrödinger's equation, but when we measure the system we find one definite outcome. The apparent jump from many possibilities to one is called collapse. This is the heart of the measurement problem. Does collapse really happen, or is it just an update to our knowledge? Interpretations of quantum mechanics differ here. Copenhagen says collapse is real in the sense that before measurement properties do not exist. Many worlds says all possibilities happen. But we only see one branch. Pilot Wave says the particle was always in one place guided by a wave. Objective collapse theory suggests there is a real physical process that forces collapse when systems get large enough. Experiments continue to probe these ideas, but so far all give the same statistical predictions. Quantum theory's probabilistic nature can be unsettling, but it is also powerful. It means that at the smallest scales events are not strictly determined, they have probabilities that can be calculated precisely. Randomness is built into the universe. This randomness is not chaos. It follows strict rules. It allows phenomena like radioactive decay, where an atom may decay in a second or a year with only probability to guide us. It shapes quantum tunneling, scattering, and interference. In classical physics, ignorance of details causes uncertainty. In quantum physics, uncertainty is fundamental. Some see this as a limit to knowledge, others as a source of richness and variety. Probability also appears in quantum statistics. Fermions like electrons obey the Pauli exclusion principle, which says no two can occupy the same quantum state. This creates the structure of atoms and the stability of matter. Bosons like photons can share states, leading to effects like lasers and Bose-Einstein condensates, where many atoms act as a single quantum wave. Statistics determine the behavior of matter from the cores of stars to superconductors. Quantum field theory unites quantum mechanics with special relativity, treating particles as excitations of fields that fill space. It predicts antimatter, explains particle creation and annihilation, and matches collider experiments. The Standard Model built from quantum field theory describes all known matter and forces except gravity. It predicted the Higgs boson decades before its discovery, yet the Standard Model is incomplete. It cannot explain dark matter, which outweighs visible matter 5-to-1, or dark energy, which drives cosmic acceleration, or why neutrinos have mass. Quantum mechanics is also central to cosmology. Quantum fluctuations in the early universe became the seeds of galaxies. Inflation theory uses quantum fields to explain the rapid expansion after the Big Bang. Even black holes are arenas for quantum effects. Hawking radiation arises from particle-antiparticle pairs near the event horizon, slowly shrinking the black hole. This leads to the information paradox. If a black hole evaporates, what happens to the information about what fell in? Resolving this may require a theory of quantum gravity. Ideas like holography suggest that information about a volume of space can be encoded on its boundary, linking gravity, quantum theory, and spacetime geometry. Quantum mechanics keeps revealing connections between areas of physics once thought separate. From the behavior of subatomic particles to the structure of the cosmos, it is both a practical tool for building technology and a deep framework for thinking about reality. Its equations describe the world with unmatched precision, yet their meaning remains open to interpretation. It challenges our senses, stretches our imagination, and shows that nature at its core is not made of solid predictable parts but of waves of probability, flashes of interaction, and patterns of correlation. The quantum world may be strange, but it is our world. Every atom in our body follows these rules. Every breath and heartbeat depends on quantum processes. The more we learn, the more we see that the line between everyday life and the quantum realm is an illusion. They are parts of the same whole, governed by the same beautiful and baffling principles. Quantum mechanics may seem like it only belongs in the minds of scientists, but its reach is far wider. It is the reason chemistry works the way it does, why materials have their specific properties, why the sun shines, and why life can exist. Inside the sun, hydrogen nuclei fuse into helium, releasing energy. Classical physics says this should not happen at the temperatures in the sun's core because the positively charged nuclei repel each other, but quantum tunneling lets them get close enough for the strong nuclear force to bind them. Without tunneling, stars would never ignite. The light from the sun travels as photons which interact with atoms in the atmosphere, scattering blue light more than red, giving the sky its color. Photons are absorbed by chlorophyll in plants starting photosynthesis. Quantum effects in the plant's proteins help transfer energy efficiently to reaction centers where it is stored as chemical bonds. This energy flows through the food chain to power life. In our own bodies, quantum mechanics governs how enzymes catalyze reactions, how our senses work, even how oxygen binds to hemoglobin. In materials science, quantum rules explain why metals are shiny, why glass is transparent, why diamonds are hard, and why graphite is soft. They describe superconductors, magnets, and semiconductors. The structure of solids is determined by the quantum behavior of electrons in a lattice. Band theory shows how electrons fill allowed energy levels and why some materials conduct and others insulate. Doped semiconductors form the basis of all modern electronics. Quantum effects also appear in liquids. Superfluid helium flows without friction, creeping up walls and through tiny cracks. Bose-Einstein condensates created at near absolute zero gather atoms into a single quantum state large enough to see, giving direct evidence of quantum behavior at a macroscopic scale. In nuclear physics, quantum forces bind protons and neutrons in the nucleus. Quantum chromodynamics explains how quarks and gluons interact inside them. The strong force is so powerful it confines quarks permanently, never letting them exist alone. In particle physics, the standard model's quantum fields produce all known particles, from electrons to the Higgs boson, each with precise properties. The Higgs field gives mass to particles through interaction. Without it there would be no atoms. Quantum theory also underlies antimatter. Each particle has an opposite with opposite charge. When they meet, they annihilate into pure energy. Antimatter is rare in the universe for reasons still unknown. This imbalance between matter and antimatter is one of physics' open questions. Cosmology uses quantum ideas to explain the early universe. Inflation theory says quantum fluctuations were stretched to cosmic scales, seeding the large-scale structure we see today. These fluctuations are recorded in the cosmic microwave background, a faint glow left from the Big Bang, in black holes. Quantum effects like Hawking radiation connect gravity to particle physics, suggesting that space and time themselves may emerge from deeper quantum structures. Theories like string theory propose that the universe is made of tiny vibrating strings, each vibration mode corresponding to a particle. Loop quantum gravity instead suggests that spacetime is made of discrete loops at the Planck scale. Both seek to unite quantum mechanics with general relativity into a theory of quantum gravity. Experiments like particle colliders and gravitational wave detectors probe these ideas, searching for new physics beyond the standard model. quantum mechanics has already given us tools to explore the universe at every scale, from the smallest particles to the largest structures. It is not just a theory of the microscopic, it is the foundation of our understanding of nature. Its equations describe reality with unmatched precision, yet its meaning remains a source of wonder. The quantum world is strange, but it is not separate from our own. It is woven into every atom, every beam of light, every living thing. It is the invisible stage on which the drama of the universe unfolds, and by studying it we not only unlock new technologies but also learn more about who we are and where we come from. Quantum mechanics tells us that the universe is not rigid and predictable but flexible and full of possibilities. That the rules of the small shape the beauty of the large, and that mystery is not a flaw but a feature of the cosmos. Quantum mechanics may seem like it only belongs in the minds of scientists, but its reach is far wider. It is the reason chemistry works the way it does, why materials have their specific properties, why the sun shines, and why life can exist. Inside the sun, hydrogen nuclei fuse into helium-releasing energy. Classical physics says this should not happen at the temperatures in the sun's core because the positively charged nuclei repel each other, but quantum tunneling lets them get close enough for the strong nuclear force to bind them. Without tunneling, stars would never ignite. The light from the sun travels as photons which interact with atoms in the atmosphere, scattering blue light more than red, giving the sky its color. Photons are absorbed by chlorophyll in plants starting photosynthesis. Quantum effects in the plant's proteins help transfer energy efficiently to reaction centers where it is stored as chemical bonds. This energy flows through the food chain to power life. In our own bodies, quantum mechanics governs how enzymes catalyze reactions, how our senses work, even how oxygen binds to hemoglobin. In materials science, quantum rules explain why metals are shiny, why glass is transparent, why diamonds are hard, and why graphite is soft. They describe superconductors, magnets, and semiconductors. The structure of solids is determined by the quantum behavior of electrons in a lattice. Band theory shows how electrons fill allowed energy levels and why some materials conduct and others insulate. Doped semiconductors form the basis of all modern electronics. Quantum effects also appear in liquids. Superfluid helium flows without friction, creeping up walls and through tiny cracks. Bose-Einstein condensates created at near absolute zero gather atoms into a single quantum state large enough to see, giving direct evidence of quantum behavior at a macroscopic scale. In nuclear physics, quantum forces bind protons and neutrons in the nucleus. Quantum chromodynamics explains how quarks and gluons interact inside them. The strong force is so powerful it confines quarks permanently, never letting them exist alone. In particle physics, the standard model's quantum fields produce all known particles, from electrons to the Higgs boson, each with precise properties. The Higgs field gives mass to particles through interaction. Without it there would be no atoms. Quantum theory also underlies antimatter. Each particle has an opposite with opposite charge. When they meet, they annihilate into pure energy. Antimatter is rare in the universe for reasons still unknown. This imbalance between matter and antimatter is one of physics' open questions. Cosmology uses quantum ideas to explain the early universe. Inflation theory says quantum fluctuations were stretched to cosmic scales, seeding the large-scale structure we see today. These fluctuations are recorded in the cosmic microwave background, a faint glow left from the Big Bang, in black. Hole's quantum effects like Hawking radiation connect gravity to particle physics, suggesting that space and time themselves may emerge from deeper quantum structures. Theories like string theory propose that the universe is made of tiny vibrating strings, each vibration mode corresponding to a particle. Loop quantum gravity instead suggests that spacetime is made of discrete loops at the Planck scale. Both seek to unite quantum mechanics with general relativity into a theory of quantum gravity. Experiments like particle colliders and gravitational wave detectors probe these ideas, searching for new physics beyond the standard model. Quantum mechanics has already given us tools to explore the universe at every scale, from the smallest particles to the largest structures. It is not just a theory of the microscopic, it is the foundation of our understanding of nature. Its equations describe reality with unmatched precision, yet its meaning remains a source of wonder. The quantum world is strange, but it is not separate from our own. It is woven into every atom, every beam of light, every living thing. It is the invisible stage on which the drama of the universe unfolds, and by studying it we not only unlock new technologies but also learn more about who we are and where we come from. Quantum mechanics tells us that the universe is not rigid and predictable but flexible and full of possibilities. That the rules of the small shape the beauty of the large, and that mystery is not a flaw but a feature of the cosmos. Quantum mechanics has not only changed science and technology but also how we think about knowledge and reality. Before the 20th century, physics was based on determinism. If you knew the present exactly, you could predict the future with perfect accuracy. Newton's laws worked for planets and projectiles and gave the impression that the universe was a vast machine. Quantum mechanics shattered that picture by showing that at the smallest scales events are not determined but have probabilities. This was not due to ignorance or faulty instruments, it was built into nature. Heisenberg's uncertainty principle said you cannot know both a particle's exact position and momentum. Schrödinger's equation described how probabilities evolve. The act of measurement selected one outcome from many possibilities. Einstein resisted this, saying God does not play dice, but experiments showed again and again that nature does. This does not mean the universe is chaotic. Quantum randomness follows precise statistical rules. It is like rolling a loaded die where you know the odds but not the exact result. This new view of reality forced scientists and philosophers to rethink concepts like causality, locality, and objectivity. In classical physics, properties exist whether we measure them or not. In quantum mechanics, some properties are not defined until measured. This raises questions about whether reality is independent of observation. The Copenhagen interpretation sidesteps the issue by focusing on what we can predict. Many worlds says all possibilities occur but in separate branches. Pilot wave theory says particles have definite properties guided by a hidden wave. Objective collapse says there is a real physical process that ends superpositions. These interpretations make the same predictions in experiments but offer different visions of reality. Quantum theory also challenges the separation between observer and system. In some interpretations, the observer becomes part of the system, entangled with it. This blurring of boundaries has inspired debates about consciousness and whether it plays a role in collapse. Most physicists treat consciousness as just another physical process, but the question remains open. quantum mechanics also shows that the universe is connected in ways classical physics never imagined. Entanglement links particles so that measuring one instantly affects the other no matter how far apart. This correlation is stronger than any classical link, and has been confirmed in countless tests. It does not allow faster than light communication, but it shows that information in the quantum world is not bound by classical separations. This has practical uses in quantum cryptography and computing, but also philosophical weight. It suggests that space may not be as fundamental as we think, that it could emerge from patterns of entanglement. Quantum mechanics has influenced other fields beyond physics. In chemistry, it explains reactions and bonding. In biology, it offers insight into photosynthesis, enzyme activity, and animal navigation. In computing, it is inspiring algorithms that use superposition and entanglement to outperform classical methods. In philosophy, it has revived debates about realism, determinism, and the role of knowledge in defining reality. Even in art and literature, quantum ideas have inspired themes of uncertainty, parallel worlds, and interconnectedness. The theory's strange mix of precise math and mysterious meaning makes it both a scientific tool and a cultural symbol. In the 21st century, quantum mechanics is at the heart of emerging technologies. Quantum computers, sensors, and communication networks aim to harness quantum states directly. This requires isolating systems from noise and controlling them with extreme precision. Progress is rapid and challenges are many, but the potential is vast. These developments echo the first quantum revolution of the early 20th century, when the theory transformed physics and led to semiconductors, lasers, and modern electronics. Now the second quantum revolution seeks to control quantum systems as easily as we control classical ones. The journey from puzzling experiments with light and metal surfaces to a theory that shapes our world shows the power of human curiosity and persistence. Quantum mechanics reminds us that nature is not limited to our intuition, that reality may be stranger than imagination, and that mystery can be a guide to discovery. It is a lens through which we can see deeper into the structure of the universe, and also a mirror reflecting the limits of what we can know. It teaches humility and wonder, showing that the smallest scales can hold the biggest surprises, and that even when the rules seem alien, they can become the foundation for understanding everything we see. The story of quantum mechanics begins with a few puzzling experiments at the end of the 19th century, when classical physics was at its peak. Scientists believed they had nearly complete knowledge of nature's laws. Newton's mechanics explained motion, Maxwell's equations explained light and electromagnetism, thermodynamics explained heat, but cracks were forming. One came from blackbody radiation. When objects are heated, they emit light. Classical theory predicted infinite energy at short wavelengths, called the ultraviolet catastrophe. Experiments did not match. In 1900, Max Planck solved the problem by assuming energy comes in discrete packets called quanta. He did it reluctantly as a mathematical trick, but it worked. His formula matched data perfectly. A few years later, Albert Einstein used the idea to explain the photoelectric effect, where light knocks electrons from metal. Classical wave theory could not explain why light below a certain frequency had no effect no matter its intensity. Einstein proposed that light is made of photons, each with energy proportional to its frequency. Only photons above a threshold can free electrons. This won him the Nobel Prize. In 1913, Niels Bohr used quantum ideas to explain the hydrogen atom, electrons could only occupy certain orbits with specific energies. When they jumped between orbits they emitted or absorbed photons. Bohr's model matched hydrogen's spectrum but failed for more complex atoms. In the 1920s, new quantum mechanics emerged. Louis de Broglie suggested particles have wave properties. Erwin Schrödinger developed wave mechanics. Werner Heisenberg developed matrix mechanics. Paul Dirac unified quantum mechanics with special relativity predicting antimatter. The new theory replaced orbits with wave functions. Probability replaced certainty. Heisenberg's uncertainty principle set limits on what can be known. The double-slit experiment showed particles can act like waves, creating interference patterns. But measurement destroys the pattern. Richard Feynman called it the central mystery. Quantum electrodynamics extended the theory to include how particles interact with light, becoming one of the most accurate theories in science. Later quantum chromodynamics described the strong nuclear force binding quarks inside protons and neutrons. The electroweak theory unified electromagnetism and the weak force. Together they formed the Standard Model, predicting particles like the W and Z bosons and the Higgs boson, discovered in 2012. Each step was driven by experiments that classical theory could not explain. Quantum mechanics also developed through thought experiments like Schrödinger's cat, highlighting the strangeness of superposition. Einstein-Podolsky-Rosen's paradox challenging completeness, and Bell's theorem proving that no local hidden variable theory can match quantum predictions. Experiments confirmed quantum entanglement and non-locality, showing that the world is connected in ways Einstein once doubted. Over the 20th century, quantum mechanics moved from theory to technology, enabling transistors, lasers, atomic clocks, and superconductors. In the 21st century it is driving quantum computers, sensors, and secure communication. Its reach extends to cosmology, where quantum fluctuations in the early universe seeded galaxies, and to biology, where quantum effects may play roles in photosynthesis and navigation. The journey from Planck's cautious equation to today's quantum engineering shows how a small change in perspective can transform science. At first quanta seemed like a temporary fix. Now they are the foundation of our understanding of nature. Quantum mechanics tells us that energy is not continuous, particles are also waves, and reality at its core is probabilistic. It challenges intuition but matches reality. It is both strange and precise, abstract and practical, unsettling and inspiring, reminding us that the universe is not bound by our expectations, and that every mystery we solve may open the door to deeper ones. The story of quantum mechanics begins with a few puzzling experiments at the end of the 19th century, when classical physics was at its peak. Scientists believed they had nearly complete knowledge of nature's laws. Newton's mechanics explained motion, Maxwell's equations explained light and electromagnetism, thermodynamics explained heat, but cracks were forming. One came from blackbody radiation. When objects are heated they emit light. Classical theory predicted infinite energy at short wavelengths, called the ultraviolet catastrophe. Experiments did not match. In 1900 Max Planck solved the problem by assuming energy comes in discrete packets called quanta. He did it reluctantly as a mathematical trick, but it worked. His formula matched data perfectly. A few years later Albert Einstein used the idea to explain the photoelectric effect, where light knocks electrons from metal. Classical wave theory could not explain why light below a certain frequency had no effect no matter its intensity. Einstein proposed that light is made of photons, each with energy proportional to its frequency. Only photons above a threshold can free electrons. This won him the Nobel Prize. In 1913, Niels Bohr used quantum ideas to explain the hydrogen atom. Electrons could only occupy certain orbits with specific energies. When they jumped between orbits, they emitted or absorbed photons. Bohr's model matched hydrogen spectrum but failed for more complex atoms. In the 1920s, new quantum mechanics emerged. Louis de Broglie suggested particles have wave properties. Erwin Schrödinger developed wave mechanics. Werner Heisenberg developed matrix mechanics. Paul Dirac unified quantum mechanics with special relativity predicting antimatter. The new theory replaced orbits with wave functions. Probability replaced certainty. Heisenberg's uncertainty principle set limits on what can be known. The double-slit experiment showed particles can act like waves, creating interference patterns. But measurement destroys the pattern. Richard Feynman called it the central mystery. Quantum electrodynamics extended the theory to include how particles interact with light, becoming one of the most accurate theories in science. Later, quantum chromodynamics described the strong nuclear force binding quarks inside protons and neutrons. The electroweak theory unified electromagnetism and the weak force. Together they formed the Standard Model, predicting particles like the W and Z bosons and the Higgs boson, discovered in 2012. Each step was driven by experiments that classical theory could not explain. Quantum mechanics also developed through thought experiments like Schrödinger's cat, highlighting the strangeness of superposition. Einstein-Podolsky-Rosen's paradox challenging completeness, and Bell's theorem proving that no local hidden variable theory can match quantum predictions. Experiments confirmed quantum entanglement and non-locality, showing that the world is connected in ways Einstein once doubted. Over the 20th century, quantum mechanics moved from theory to technology, enabling transistors, lasers, atomic clocks, and superconductors. In the 21st century, it is driving quantum computers, sensors, and secure communication. Its reach extends to cosmology, where quantum fluctuations in the early universe seeded galaxies, and to biology, where quantum effects may play roles in photosynthesis and navigation. The journey from Planck's cautious equation to today's quantum engineering shows how a small change in perspective can transform science. At first, quanta seemed like a temporary fix. Now they are the foundation of our understanding of nature. Quantum mechanics tells us that energy is not continuous, particles are also waves, and reality at its core is probabilistic. It challenges intuition but matches reality. It is both strange and precise, abstract and practical, unsettling and inspiring, reminding us that the universe is not bound by our expectations, and that every mystery we solve may open the door to deeper ones. By the mid-20th century, quantum mechanics had become the foundation of modern physics, yet its meaning was still debated. Scientists accepted its accuracy but argued about its interpretation. Some, like Niels Bohr, embraced the Copenhagen view, focusing on measurement and probabilities. Others, like Albert Einstein, insisted it was incomplete and that hidden variables would one day restore determinism. John Bell's theorem in 1964 showed that if hidden variables exist, they must be non-local, allowing instant connections across space. Experiments in the 1970s and beyond confirmed quantum predictions and ruled out local hidden variables, proving that entanglement is real and stronger than classical physics allows. Meanwhile, quantum theory expanded into quantum field theory, uniting special relativity and quantum principles. It treats particles as excitations of underlying fields that fill all space. Each type of particle comes from its own field, the photon from the electromagnetic field, electrons from the electron field, quarks from quark fields, gluons from the strong force field. Quantum field theory explains particle creation and annihilation, predicts antimatter, and underlies the Standard Model, which has been tested to extreme precision. The Standard Model includes the electromagnetic, weak, and strong forces but not gravity. It predicts particles like the Higgs boson, which was finally observed in 2012 at CERN, confirming how particles gain mass, yet the Standard Model leaves mysteries. It does not explain dark matter, dark energy, or why neutrinos have mass. It does not unify gravity with the other forces. Attempts to solve these gaps include string theory, which says particles are tiny vibrating strings, and loop quantum gravity, which says spacetime is made of discrete loops. Both remain unproven. Black holes push quantum theory to its limits. Stephen Hawking showed they emit radiation due to quantum effects near the event horizon, meaning they can slowly evaporate. This creates the black hole information paradox. If they vanish, what happens to the information about what fell in? Some theories suggest information is preserved in a scrambled form, others link it to holographic principles, saying information in a volume can be encoded on its boundary. Quantum mechanics also plays a role in cosmology. Quantum fluctuations in the early universe became seeds for galaxies. Inflation theory uses quantum fields to explain the rapid expansion after the Big Bang. Observations of the cosmic microwave background match these predictions. Quantum mechanics has also inspired new technologies in the second quantum revolution. Unlike the first, which used quantum-explained effects like semiconductors and lasers, the second seeks to directly control quantum states. Quantum computers use qubits in superposition and entanglement to solve problems faster than classical computers. Quantum cryptography uses the fact that measurement disturbs quantum states to detect eavesdropping. Quantum sensors use interference to measure time, gravity, and magnetic fields with extreme precision. These advances require controlling decoherence and noise, but progress is steady. Beyond science, quantum mechanics has influenced culture, inspiring metaphors for uncertainty, multiple realities, and interconnectedness in literature, art, and film. It has also shaped philosophy by challenging realism, determinism, and the nature of observation. Some interpretations, like many worlds or pilot wave, aim to restore a more concrete reality. Others embrace indeterminacy. All agree on the math and predictions. What changes is the story we tell about what is happening. Quantum mechanics is both a tool and a mystery. It allows us to build the most precise devices and yet leaves us wondering what reality is. It teaches that knowledge has limits, that the universe is richer than common sense suggests, and that even the smallest scales can hold surprises that reshape our view of everything. Quantum mechanics is not only a set of equations but also a way of seeing the world. It tells us that matter and energy are not separate things but can change into one another, that particles are not tiny billiard balls but excitations of invisible fields, that waves are not just ripples in water but probabilities guiding where particles might be. It says that nothing is truly isolated. Everything interacts and can become entangled, that measurements do not just reveal reality but help shape it. This vision has changed how scientists think about everything from the birth of the universe to the structure of atoms. In the early universe, quantum fluctuations were stretched across space during inflation, creating slight differences in density that grew into galaxies and clusters. The cosmic microwave background is a snapshot of these quantum seeds frozen in light. Even the vast structure of the cosmos has its roots in tiny quantum events. In the lab, physicists use quantum control to make Bose-Einstein condensates, macroscopic quantum states that let us see wave behavior at a human scale. Superconductors and superfluids show that quantum rules can dominate on large scales under the right conditions. Quantum coherence is the ability of a system to maintain a definite phase relationship between states. It is fragile and easily lost through decoherence when a system interacts with its environment. Controlling decoherence is one of the main challenges for quantum computers. Quantum error correction is a method to protect quantum information from noise by spreading it across entangled qubits. Progress here is key to building scalable machines. Quantum communication uses entanglement to share information in a way that reveals any tampering. Satellite experiments have shown entangled photons can be sent over thousands of kilometers, hinting at future global quantum networks. Quantum sensing uses interference to measure tiny changes in gravity, acceleration, and time, aiding navigation, geology, and fundamental physics tests. These are examples of the second quantum revolution. The first gave us tools by understanding quantum principles, the second gives us power by controlling quantum states directly. Yet even as we harness quantum effects, we do not fully understand them. Interpretations still differ on whether the wave function is a real physical object or just a mathematical description, whether collapse is real or just apparent, whether reality splits or remains whole. These are not just philosophical questions but could influence how we design experiments. Some proposals aim to test collapse models by looking for tiny random motions in massive systems. Others search for quantum gravity signatures in black hole behavior or the early universe. Quantum mechanics also changes how we think about time. In classical physics, time is a background ticking forward evenly. In relativity, it is flexible and linked to space. In some quantum gravity ideas, time might not be fundamental but emergent from correlations between events. Experiments with atomic clocks already show time flows at different rates in different gravitational fields. On mountaintops, clocks run slightly faster than at sea level. Quantum theory may eventually tell us whether time itself has a quantum nature. Despite its mysteries, quantum mechanics is a practical science. It drives industries from electronics to medicine. It makes possible GPS, MRI, lasers, and solar cells. It is not an abstract curiosity but a foundation of the modern world, yet it remains a reminder that knowledge is never complete, that the closer we look the stranger reality becomes. Quantum mechanics teaches humility in the face of nature's complexity and wonder at its elegance. It shows that certainty is rare, connection is deep, and that even in apparent chaos there are patterns we can understand and use. It invites us to see the universe not as a static machine but as a dynamic web of possibilities always in motion. Quantum mechanics has grown from a strange fix for experimental puzzles into a central pillar of science. Its journey shows how curiosity, persistence, and open-mindedness can reshape our view of reality. In the late 19th century, physics seemed complete. Newton's laws and Maxwell's equations described the world with great success, but phenomena like blackbody radiation and the photoelectric effect refused to fit. Max Planck's quantization of energy in 1900 was the first crack in the wall. Albert Einstein's photon theory of light in 1905 made the gap wider. Niels Bohr's atomic model in 1913 built on these ideas. In the 1920s, quantum mechanics took full form with the work of Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others, introducing wave functions, uncertainty, and probability. Experiments like the double slit showed particles can behave like waves and waves like particles. By mid-century, quantum electrodynamics and later quantum chromodynamics extended the theory to cover electromagnetism and the strong force. The electroweak theory unified electromagnetism and the weak force, together forming the Standard Model, tested to extraordinary precision. Yet quantum mechanics was never just about equations. It raised deep questions about reality. Does the wave function represent something real or just our knowledge? Does measurement create outcomes or reveal them? Are there many worlds or one? Is collapse a physical process or an illusion? Debates between Bohr, Einstein, and others set the stage for decades of discussion. Bell's theorem in 1964 proved that no local hidden variables can match quantum predictions. Experiments confirmed entanglement, showing nature is non-local in a way that defies classical ideas. Quantum theory also revealed that empty space is not empty but filled with fluctuating fields. Particles can appear and disappear in pairs. These quantum fluctuations may have shaped the early universe, giving rise to galaxies and cosmic structure. Black holes test quantum theory's limits. Hawking radiation links them to thermodynamics and raises the information paradox. Attempts to unify quantum mechanics with general relativity have led to ideas like string theory and loop quantum gravity, neither proven but both guiding research. The second quantum revolution now focuses on controlling quantum states. Qubits in superposition and entanglement power quantum computers, which may solve problems classical machines cannot. Quantum communication promises secure channels where eavesdropping is detectable. Quantum sensing enables measurements of time, gravity, and magnetic fields with extreme precision. These advances depend on mastering decoherence, using quantum error correction, and developing scalable systems. Quantum mechanics also influences other sciences. In chemistry, it explains bonds and reactions. In biology, it may underlie photosynthesis, enzyme activity, and animal navigation. In cosmology, it shapes theories of the Big Bang and cosmic inflation. In technology, it powers semiconductors, lasers, and atomic clocks. It is hard to imagine modern life without it, yet it still resists a single clear interpretation. Perhaps this is its greatest lesson, that reality can be fully predictable in experiment but remain mysterious in meaning. Quantum mechanics invites us to accept uncertainty not as ignorance but as a fundamental feature of nature. It shows that the universe is a web of probabilities, connections, and possibilities, that even the smallest scales can influence the largest, and that by studying the strange we can discover the useful. It reminds us that science is not about final answers but about better questions, and that sometimes the path to understanding begins with admitting we do not yet understand. Quantum mechanics continues to shape the future through what scientists call the second quantum revolution. The first revolution in the early 20th century gave us the theory itself and technologies like semiconductors, lasers, and magnetic resonance. The second aims to control individual quantum systems with precision. Quantum computers use qubits that can exist in superposition, meaning they can be both 0 and 1 at the same time. They also use entanglement, which links qubits so that the state of one instantly affects the other. This allows certain problems to be solved exponentially faster than on classical computers. Algorithms like Shor's for factoring large numbers and Grover's for searching databases show the potential power. Quantum error correction is essential because qubits are fragile and can lose their state through decoherence. Techniques encode information across multiple qubits so that errors can be detected and fixed without measuring the quantum data directly. Quantum communication uses entanglement to create secure channels. If an eavesdropper tries to intercept, the quantum state changes and the intrusion is detected. Experiments have sent entangled photons over hundreds of kilometers through fiber and even between ground stations and satellites, hinting at global quantum networks. Quantum sensing exploits interference and superposition to measure tiny changes in time, gravity, and magnetic fields. Atomic clocks based on quantum transitions now keep time so accurately they would drift less than a second over the age of the universe. These clocks improve GPS, test relativity, and search for changes in fundamental constants. Quantum gravimeters can detect underground structures. Quantum magnetometers can map brain activity. The challenge in all these technologies is controlling quantum states in the presence of noise from the environment. Advances in cryogenics, vacuum systems, and isolation help, as do better materials and control electronics. Beyond technology, quantum mechanics is also a tool for probing nature's deepest laws. Particle accelerators smash particles together to explore higher energies where new physics may appear. Cosmologists use quantum theory to understand the early universe, and experiments look for quantum effects in gravity. Theories like string theory suggest extra dimensions and vibrating strings. Loop quantum gravity suggests spacetime itself is quantized. Other ideas propose that spacetime could emerge from patterns of entanglement. Black holes may hold clues. Hawking radiation shows they are not completely black, but the fate of information that falls in remains an open question. Resolving it may require a quantum theory of gravity. Quantum mechanics also challenges our understanding of time. In classical physics, time is a steady background. In relativity, it is relative to speed and gravity. Some quantum gravity approaches suggest time could be emergent from correlations, meaning it may not exist. At the most fundamental level, experiments with atomic clocks already reveal time runs differently at different heights in a gravitational field. Quantum mechanics shows that even familiar concepts like cause, effect, and sequence may be more flexible than they appear. The quantum world is not a distant realm but the foundation of everything. Every atom in our body follows quantum rules. Every chemical reaction, every photon of light, every signal in electronics is guided by them. Learning to control quantum systems is like learning a new language nature has always spoken. It opens doors to technology we cannot yet imagine and to understanding the universe in ways we have never seen. It reminds us that the line between science fiction and science fact is often just a matter of time and persistence, and that curiosity remains the most powerful tool we have for exploring the unknown. Quantum mechanics also reaches into areas where science and philosophy meet. It forces us to think about what reality really is and how we can know it. In classical physics, the world exists with definite properties whether or not we look. In quantum mechanics, some properties are undefined until measured. This raises the question of whether observation creates reality or just reveals it. The Copenhagen interpretation says quantum theory only tells us the probabilities of measurement results, and that it is meaningless to talk about properties before measurement. Many worlds says all possible outcomes happen but in different branches of the universe. Pilot wave theory says particles always have definite positions guided by a wave. Objective collapse theories say superpositions end through a physical process. Each view gives the same experimental predictions but paints a different picture of the universe. Experiments are being designed to test the differences, for example looking for spontaneous collapse in large systems or interference patterns in macroscopic objects. Quantum mechanics also challenges locality, the idea that objects are only affected by their surroundings. Entangled particles can have linked properties even when far apart. Measuring one instantly changes the prediction for the other. This does not send information faster than light, but it does suggest that the universe is more connected than classical physics allows. Entanglement has been confirmed by Bell test experiments and is now used in quantum communication. Another philosophical challenge is the role of probability. In classical physics, probability comes from ignorance. In quantum physics, it is built into nature. Some see this as meaning the universe is inherently indeterminate. Others think hidden variables might restore determinism. Quantum mechanics also blurs the line between cause and effect. In some quantum processes, it is hard to say which event caused the other, and in certain experiments the order of events can be in superposition, raising questions about whether time has a fixed direction. Quantum theory even influences ideas about consciousness. Some suggest it might involve quantum processes in the brain, though most neuroscientists see no evidence for this. Still, the connection between observer and system keeps the question alive. Quantum mechanics is not just about tiny particles. It also shapes the universe as a whole. Quantum fluctuations in the early cosmos may have seeded galaxies. Inflation theory uses quantum fields to explain the universe's rapid early expansion. Black holes mix quantum physics with gravity in ways we do not yet fully understand. Holographic principles suggest that all the information in a region can be stored on its boundary, linking quantum theory to the geometry of space. Quantum mechanics has also become a tool for discovery beyond physics. In chemistry, it explains bonding. In biology, it helps describe processes like photosynthesis and enzyme activity. In materials science, it guides the design of superconductors and semiconductors. In technology, it powers lasers, transistors, atomic clocks, and emerging quantum computers. In philosophy, it challenges determinism and realism, showing that our deepest assumptions about reality may be incomplete. It teaches that certainty is rare, connection is deep, and possibility is fundamental. Quantum mechanics is not just a set of rules for scientists, it is a reminder for everyone that the universe is richer and stranger than it looks, that our knowledge will always be partial, and that exploring the unknown is part of what makes us human. Quantum mechanics also teaches us that scale changes everything. At the human scale, objects have definite positions and speeds. cause and effect seem clear, and time flows in one direction. At the quantum scale, particles can be in more than one place at the same time, they can interfere with themselves, and their properties can be undefined until measured. This is not because our tools are weak but because nature itself works this way. The strange behavior is usually hidden because quantum effects are fragile and get washed out when particles interact with their surroundings. This process called decoherence explains why we do not see macroscopic objects in superpositions. Controlling decoherence is one of the main challenges in building quantum technology. When systems are well isolated, we can see quantum rules in action even at large scales. Superconductors carry current with zero resistance because electrons form paired states that move without scattering. Superfluids flow without friction and can climb walls. Bose-Einstein condensates put thousands of atoms in the same quantum state, making them act as a single giant wave. These systems help scientists test quantum theory in regimes that are hard to reach with single particles. They also open doors to new applications like ultra-sensitive sensors and quantum simulations. Quantum simulations use controllable quantum systems to model other quantum systems that are too complex for classical computers. For example, ultra-cold atoms in optical lattices can mimic the behavior of electrons in solids, letting researchers explore superconductivity and magnetism. Trapped ions can simulate quantum chemistry. These tools are valuable because many body quantum problems are extremely hard to solve mathematically. Quantum mechanics also plays a role in the stability of matter. The Pauli exclusion principle says no two fermions like electrons can occupy the same state. This keeps electrons from collapsing into the nucleus and gives matter its volume. Without it, atoms would be tiny and the world as we know it would not exist. Quantum forces also shape the periodic table, giving elements their chemical properties. Photons and other bosons follow different rules. They can share states leading to effects like laser light where many photons move in phase. The balance between fermion exclusion and boson grouping helps explain the structure of the universe. In astrophysics, quantum mechanics explains why white dwarfs and neutron stars do not collapse under gravity. Electron and neutron degeneracy pressures resist compression. Black holes form when gravity overwhelms even these quantum pressures. In cosmology, quantum fluctuations in the early universe seeded the structures we see today. Without them, the cosmos would be smooth and lifeless. In technology, quantum principles are everywhere. From the LEDs in screens to the transistors in computers to the GPS that depends on atomic clocks, noise cancelling. Headphones use interference. MRI scanners use nuclear spin. Lasers scan barcodes and perform surgeries. Each of these works because quantum mechanics describes how light and matter interact, yet for all its success, quantum mechanics remains incomplete. It does not explain gravity, dark matter, or dark energy. It leaves open questions about the nature of measurement and reality. It hints that spacetime might emerge from deeper quantum structures, and it challenges our ideas about determinism and causality. Studying it is not only about making better devices but also about understanding the rules of existence. Quantum mechanics is a reminder that even the smallest things can have the biggest impact, that the universe at its core is governed by laws that are strange, precise, and beautiful, and that by exploring them we learn not just about the world outside us but also about the limits and possibilities of human thought. Quantum mechanics also shows us that the universe is built from interactions, not from isolated pieces. In classical thinking, objects exist on their own and then interact. In quantum thinking, the act of interaction can define what the objects are. Particles can be entangled so that their properties are linked even when far apart. Measuring one changes the prediction for the other instantly. This link is stronger than any classical correlation and is confirmed by experiments again and again. It does not send information faster than light, but it does mean that the universe cannot be explained by purely local rules. This non-locality is a fundamental part of quantum theory. It also connects to the idea that space and time themselves may not be basic ingredients of reality but may emerge from deeper quantum relationships. In some approaches to quantum gravity, spacetime is a network of entangled quantum states. Geometry is a large-scale pattern formed by microscopic links. This could explain why gravity is so hard to fit into quantum theory, because gravity might not be a force in the same way as electromagnetism or the strong force, but a property that emerges from the way information is organized. The holographic principle takes this further, saying that the information about everything inside a region can be stored on its boundary. This idea comes from studying black holes, where the entropy is proportional to the surface area, not the volume. If true, it could mean that our three-dimensional world is like a projection from a deeper two-dimensional structure. These are bold ideas and not yet proven, but they fit well with some results from string theory and quantum field theory. Quantum mechanics also plays a role in the limits of measurement. The uncertainty principle says there is a limit to how precisely certain pairs of properties like position and momentum can be known. This is not a flaw in instruments but a feature of reality. It means that at small scales the concept of a precise trajectory like a ball's path does not exist. Instead, we can only talk about probabilities. Quantum limits also appear in time measurement. Atomic clocks reach precision set by quantum rules. Surpassing them requires using entanglement or squeezing states to reduce uncertainty in one quantity at the expense of another. These quantum-enhanced measurements are already being used in gravitational wave detectors to improve sensitivity. Quantum mechanics also shapes the future of computing. Quantum algorithms use superposition and entanglement to process information in ways classical computers cannot. They may one day factor large numbers quickly, simulate complex molecules for drug design, or optimize massive systems, but they are not just faster versions of current computers. They work in fundamentally different ways. Understanding their strengths and limits is an active area of research. Quantum networks could link quantum computers into a web that shares entanglement and enables new forms of secure communication. All of these depend on controlling quantum states against noise and decoherence, something nature makes very challenging, yet progress is steady. Each year brings more qubits, better coherence times, and more sophisticated error correction. Quantum mechanics also continues to inspire philosophy and art. Its ideas about uncertainty, multiple realities, and deep connection appear in novels, films, and paintings. It challenges the way we tell stories about reality and possibility. It suggests that the universe is not a fixed stage but a dynamic flow of potential outcomes, some realized, some not, and that we are part of this unfolding. As observers, we are woven into the fabric of events, not standing outside them. Quantum mechanics is both a scientific theory and a lens for thinking about existence. It tells us that the smallest things matter, that connections can be invisible yet powerful, and that reality may be far richer than we can imagine. Quantum mechanics also reshapes how we understand energy and matter at the most basic level. In classical physics, energy can take any value and matter is made of solid particles. In quantum physics, energy comes in discrete amounts and particles are excitations of underlying fields. Light is not just a wave but also made of photons. Electrons are not just particles but also waves that spread out and interfere. This wave-particle duality is not a contradiction but a sign that our categories are incomplete. Quantum mechanics says that nature uses probabilities. The wave function tells us the chance of finding a particle in a certain place or with a certain momentum. When we measure it, the wave function appears to collapse to a single outcome. The process of measurement is still one of the most debated parts of the theory. Some interpretations say the collapse is real, others say it is just a change in our knowledge. Still others say all possible outcomes happen in different branches of the universe. No matter the interpretation, the predictions match experiments with incredible accuracy. Quantum mechanics also shows that vacuum is not empty but full of fluctuating fields. Virtual particles appear and vanish constantly. This quantum vacuum has measurable effects like the Casimir force between plates and the Lamb shift in atomic spectra. These fluctuations may even be connected to dark energy, which drives the expansion of the universe. In cosmology, quantum theory explains how tiny fluctuations in the early universe became seeds for galaxies. Inflation theory says these quantum ripples were stretched to cosmic scales. The cosmic microwave background still carries their imprint. Black holes are another place where quantum physics and gravity meet. Hawking radiation shows that black holes are not eternal but slowly lose mass. This leads to the information paradox. If they evaporate, what happens to the information about what fell in? Solving this may require a complete theory of quantum gravity. Ideas like the holographic principle and string theory offer possible answers, but none are proven. In technology, quantum mechanics is behind almost every modern device: transistors in computers, lasers in communication, atomic clocks in GPS, MRI machines in hospitals, and LEDs in lighting all work because of quantum rules. The second quantum revolution is now aiming for devices that directly exploit superposition and entanglement: quantum computers, quantum sensors, and quantum communication systems are being developed worldwide. They promise new capabilities but also face challenges in scaling, stability, and error correction. Progress here requires advances in materials, cryogenics, and control systems. Quantum mechanics also affects fundamental limits in measurement and communication. The no-cloning theorem says you cannot make an exact copy of an unknown quantum state. This is what makes quantum cryptography secure. Quantum metrology uses entangled states to push measurement precision beyond classical limits. Gravitational wave detectors already use squeezed light to improve sensitivity. These examples show that quantum mechanics is not only about theory but about practical tools that shape our lives, yet it also remains a source of deep mystery. We know how to use it but not fully what it means. It challenges our ideas about reality, determinism, and causality. It suggests that space and time may be emergent and that the universe is more connected than it appears. Studying it is not only about making better machines but about exploring the foundations of existence. Quantum mechanics is both a map and a puzzle, guiding us to new discoveries while reminding us that the universe is stranger than we can imagine. It shows that knowledge is always expanding and that the frontier of understanding is where science and wonder meet. Quantum mechanics also gives us a new way to think about information. In classical physics, information is stored in bits that are either 0 or 1. In quantum physics, information can be stored in qubits that can be in a superposition of 0 and 1 at the same time. When qubits are entangled, the state of one cannot be described without the other, no matter how far apart they are. This is what makes quantum information different and powerful. It allows certain computations to be done more efficiently. Then on classical machines, it also allows new types of secure communication where any attempt to intercept changes the state and reveals the intrusion. Quantum teleportation is a process where the state of a qubit is transferred from one place to another using entanglement in classical communication. No matter the distance, the qubit itself does not travel, but its state is recreated. This has been demonstrated over hundreds of kilometers and even between ground and satellites. It could be the basis of a future quantum internet. Quantum mechanics also changes how we think about copying information. The no-cloning theorem says an unknown quantum state cannot be perfectly copied. This sets fundamental limits on how information can be stored and transmitted. In quantum computing, algorithms like Shor's and Grover's show speedups for specific problems. But building large-scale quantum computers is challenging. Qubits are fragile and lose coherence due to interaction with their environment. Quantum error correction protects information by encoding it across multiple qubits so that errors can be detected and fixed without measuring the data directly. Progress here is steady with new milestones each year. Quantum mechanics also inspires new ways of measuring time and space. Atomic clocks based on quantum transitions are so precise they can detect differences in gravity between your head and your feet. Quantum sensors use interference to detect tiny changes in motion, fields, or forces. These tools are being developed for navigation, geology, and medical imaging. Quantum theory also touches on the limits of knowledge. The uncertainty principle means some properties cannot be known at the same time with arbitrary precision. This is not a flaw but a rule of nature. It shapes how we design experiments and how we think about reality. Quantum randomness is also truly random. Unlike classical randomness, which comes from ignorance, this makes quantum random number generators useful for cryptography and simulations. Quantum mechanics is also linked to thermodynamics. Concepts like entropy, temperature, and work have quantum versions. Quantum thermodynamics studies how these rules change at small scales and how quantum effects can be used in engines or refrigerators. Black hole thermodynamics is an area where quantum theory, gravity, and thermodynamics meet. It suggests deep connections between information, energy, and spacetime. Quantum mechanics also invites us to think about the future. As we build better quantum devices, we may discover new phenomena that current theory does not explain. Just as the study of light led to quantum theory in the first place, quantum mechanics is a reminder that our understanding is never final, that every answer can lead to more questions. It tells us that the universe is not fixed but full of possibilities. That knowledge is shaped by how we interact with the world, and that by exploring the smallest scales we can unlock the biggest mysteries. Quantum mechanics leaves us with both answers and questions. It explains how the smallest parts of the universe behave and why matter, energy, light, and forces act the way they do. It has given us the technology that powers modern life, from computers to medical imaging. from GPS to lasers, from solar panels to communication systems. It has revealed that the universe is not a clockwork machine but a web of probabilities, connections, and possibilities. It shows that particles can be waves, that energy comes in quanta, that observation affects outcomes, and that entanglement links distant things in ways that defy classical ideas. It challenges our sense of certainty and invites us to think in new ways. It tells us that at the deepest level the rules are strange yet exact, unpredictable in detail yet precise in pattern. It also tells us that there is much we do not yet know. We do not fully understand the nature of measurement, the meaning of the wave function, or the link between quantum mechanics and gravity. We do not know what dark matter and dark energy are, or whether spacetime is fundamental or emergent. These open questions are not signs of failure but signs of a living science, a map that is still being drawn. Quantum mechanics also teaches us about the nature of knowledge itself. It shows that limits are real, that some things cannot be known together with infinite precision, that uncertainty is not ignorance but part of reality. It shows that possibilities exist until they are resolved, that reality may branch into many worlds, or that outcomes may emerge through deeper rules we have yet to discover. The journey from Planck's equation to quantum computers has taken little more than a century. In that short time our view of the universe has changed completely, and the pace of change is not slowing. New experiments are testing quantum effects in larger systems. New theories are trying to unify the quantum and the cosmic. New technologies are pushing the limits of control and precision. We are learning not only how to describe the quantum world but how to shape it. This is the heart of the second quantum revolution. It is a moment where understanding meets capability, where curiosity becomes creation. Quantum mechanics will continue to challenge our minds and expand our tools. It will keep revealing that the universe is deeper, stranger, and more beautiful than we can see at first glance. It will keep reminding us that mystery is not the opposite of knowledge but its partner, and that science is not the end of wonder but its greatest source. In the end, quantum mechanics is not just about particles, waves, and equations. It is about the story we tell of the universe and our place in it, a story where uncertainty is a feature, where possibility is real, and where the smallest things can change everything. It is about the human drive to ask questions even when the answers are strange, to keep exploring even when the path is unclear, and to see in every puzzle not a wall but a door. The quantum world is not far away, it is here in every atom of our bodies, every spark of light in our eyes, every signal in the devices we use. We live in it, we are part of it, and as we keep learning its rules we are also learning about ourselves, our limits, and our potential. The journey is far from over, and the next chapter will be written by the questions we dare to ask and the experiments we dare to try, in quantum mechanics. As in life, the unknown is not something to fear, it is where the future begins.